Hello everyone, I'm Pingbang, and today I want to talk about one of our recent work on scalable influence function with sparse gradient compression, which is published in New Year's 2025. And this is a joint work with Joe, Weijing, Han, and also Jiaqi. So as the subtitle suggests, we're going to talk about efficient data attribution and also influence function. Like to set a tone for this talk, I'm going to stay on high level and also provide a lot of illustration and intuition. So hopefully, even if you are not familiar with the literature of data attribution or influence function, you can follow all the talk. So let's get started. First, I want to motivate our work, which is probably the only slide that might not make sense to you if you are not familiar with data attribution, but I promise this is the only exception. So what's the motivation here? Most of the popular data attribution methods are gradient based. So for example, the famous influence function, track, or like more recently, let's say training dynamic aware method like SGD influence, data volume embedding are all like in this category. So they're expensive and both computation wise and memory wise. And the goal of this talk is to introduce all the common tricks for speeding up gradient-based data attribution method. In particular, we're going to talk about first, how to approximate the hashing, and second, how to do gradient compression. And the second point is actually our focus. So this is this work. And as a running example, we're going to use influence function, but the underlying principles of what we're going to talk about will generalize to like other methods. So first, let me give you like crash course on data attribution, or more specifically, influence function. So data attribution tries to quantify counterfactual effects for dataset perturbation. So what do I mean by that? So first, let's set up some notation. Say we have a model, theta D, trained on a training set D, where we will use P as the number of model parameters and N as the number of data points throughout the talk. And let's say we're given a quantity of interest, which is termed as target function in the literature. And to think about this, you should think about like validation loss. So given a training data set, you're going to first train a model and evaluate the validation loss on this model. So this F depends on D. And the goal of data attribution is to predict how this target will change if the training data set D is counterfactually perturbed to D prime. So basically, we're trying to estimate this difference between f of D prime and f of D. So why counterfactual? The counterfactual aspect of this is we are not actually going to retrain a model every time when we're given a perturbed data set D prime. Instead, we're trying to like approximate this effect given that we have, let's say, an access to theta D only, but not like theta D prime. So this is like counterfactually, we are thinking about what if the data set is D prime, but not D. So how can you do this? Or like, what's the first step to tackle this problem? So the popular method study this from a fine-grained, localized viewpoint. Specifically, we will consider D prime of a particular form, which is D minus B, where B is a small batch of samples. So think about what will happen if we remove, let's say, this 10 points from our training set. How will that affect our validation loss? And for each possible B, if we can predict this theta F, delta F, then we can basically reason on a lot of different things. For example, whether I need to filter out these samples or I should select these samples, right? Because we can observe what the validation loss will change based on our, like, let's say, removal or addition on the subset. So more popular choices of B is actually singleton set. So we just consider what if we remove one data point or add one data point. So this will provide point-wise effect. So this is like the problem setup. And the next question you should ask is, how can we tackle this, right? So to see how can one tackle this problem, it's, let's say, it's natural or it's beneficial to think about we parameterize the data set by weight. So specifically, we should think about, let's say, each data point now receives an initial weight of 1 over n. So they, in total, they sum up to 1. Okay? If we parameterize the data set in this way, then we can view the model trained on the data set or weighted data set to be a function of this weight. So if we write out the, let's say, the empirical risk minimization, then theta W will be argmin of the weighted per sample loss, right? So this is like Li is our per sample loss, which is defined here. And we weighted each I with their own data weight, Wi. So if we think about the model trained on this like weighted function or trained on this like weighted data set as a function of weight, then what we can do is we can think about perturbation of the data point as perturbation on the weight. Then we can use calculus, for example, Taylor expansion to expand this function around the default weight. So we can basically study the first order change or infinitesimal change on what if we perturb the weight a little bit. So in figure, it looks something like this. Initially, each data point receives 1 over n weight, and we will put this weight to our learning algorithm. It will learn some minimizer, which will return like theta 1 over n. And now, what if we perturb the weight a little bit? Let's say now it is d prime, which corresponds to weight w prime. So this is the perturbed weight. Then the learning algorithm will give us a slightly different minimizer, theta w prime, and we are interested in estimate how will this theta 1 over n change to this like theta w prime. Or you can also think about this as how can we approximate this on theta w prime, right? So to study that, well, we will fall back to our like popular choice, which is like, let's just consider pointwise perturbation. So this is exactly what I wrote. This is just like pointwise perturbation where we are thinking about, we are removing one data point, which will basically correspond to removing 1 over n weights for zi. So you can formalize this as d plus epsilon zi, where epsilon now is like minus 1 over n. So we're removing 1 over n weights from zi. So it's totally gone, basically. And now, if you view this as a function of w, then we can basically do like first order approximation, namely Taylor expansion, which is just like simple calculus. We're just trying to reason or trying to estimate this effect from first order, which is basically just this. You can pause a bit if you are not convinced, but this is basically just freshman calculus. And you can like, if you have like delta f written in this form, then the next question is how can you estimate this? And if you write this down, this is basically just given by chain rule, which is then the gradient of f times the infinitesimal change on this model, the function of this like perturbed weight. Yeah, so I'm not going to like explain this in full detail, but basically this is just like chain rule. And now the question is, this is like well understood, right? This is just gradient of f, but now how can we compute this, right? This seems like complicated to estimate. So influence function basically tells you how to estimate that. Given like some technical condition, for example, convex loss, so minimizer will always be unique, you can basically compute this in closed form, which is given by minus hash and inverse times per sample gradient. So in picture, it looks something like this. So first, we are thinking about, we are just perturbing the data points ith weights by epsilon, and we pass this and we get this, the perturbed minimizer. And the influence function basically tells us how to estimate this change, which is given by basically epsilon times the infinitesimal slope of change on the model weight or the model parameter, which is minus hash and inverse times per sample gradient. So that's basically influence function. And now we should ask, okay, but how can we compute this, right? This seems like still a little bit complicated. So let's look into that. So the main computation, after you stare at this for a while, you will see the main computation should be the second part, which is the so-called inverse Hessian vector product, or IHVP. The inverse Hessian correspond to this part, vector correspond to this per sample gradients, and product corresponding to like this multiplication. And why is that? It's because once IHVP is solved, so basically you compute this for every I, then you can compute the influence by inner product with your gradients of f. right? And in the product, it's like very efficient. So the main computation should be this IHVP. And to understand the problem size, the perceivable gradient is like a size p gradient or a size p vector. And the inverse Hessian is like basically a p times p matrix. And in order to compute this, we're going to invert and p times p second order Hessian. Okay. So see like these two basically forms the bottleneck of this computation, right? So first, computing all vectors, which is computing all the perceivable gradients, requires OMP because for each sample, we are going to do forward-backward passes, which takes OP, and there are n data points. And for computing inverse Hessian, you're going to first form the Hessian, which takes like roughly p squared, and then you're going to invert it, which takes roughly p cubed. And for computing products, this is basically just inverse Hessian times the vector, which is p squared. And now you have like n data points. So n perceivable gradients, you need to do this. So it's in total OMP squared. And on the other hand, storing this result is also challenging. And this is because, for example, to store all the vectors, it will require OMP as well. And storing the inverse Hessian will also require OP squared. So in total, like computation-wise, inverse Hessian is the main bottleneck. And for storage, vectors and also storing the inverse Hessian are both like challenging. Like n can be like roughly p or even more than p. So now let's talk about how can one accelerate IHVP computation. But before I do that, I want to make a small remark on the history of IHVP because this is actually a general problem. And for example, it arises in stochastic optimization or like second order optimization problem. You should read this as like IHVP in this context is trying to compute, let's say, condition gradient. So if you look back, like, yeah, so this is like you're computing the condition gradients conditioned by the inverse Hessian. Okay? And so techniques to accelerate IHVP computation has been developed because of like this is quite general and you are bumping to this problem in optimization context all the time. And notably, this techniques aims to directly compute IHVP, or you should think about this as they require using the result of IHVP literally. So think about you are going to compute IHVP and use the result of IHVP directly to update your model. And so, for example, the famous algorithm in this regime or in this category are, let's say, Lisa data int, which basically tries to avoid performing large matrix inverse. However, like they tend to be slow and cannot be scaled up. And why we spend all the time talking about this is because IHVP in our context, which is influence function computation, is quite specific and special. And we'll see why this is the case in a second. But basically, we view this like classical literature as like orthogonal to what we are going to talk about, which the reason might be like a little bit unclear for now, but I promise this will be like clear for a second. So this is just like a historical note. And now we're going to talk about two of our like main techniques to accelerate HVP in our context, which is computing influence function. First is Hessian approximation. So to mitigate the bottleneck of computing inverse Hessian, there's a famous theorem we can use. So the theorem tells us that if we are training our model using cross entropy loss, then in exploitation, this empirical FIM or feature information matrix will equal to our Hessian, where the feature information matrix is the outer product of all perceivable gradient, and we take average of all of them. So you can think about this as like measuring the covariance between the perceivable gradient. So we should think about, okay, then sure, we can replace Hessian by FIM, but does this help? We see that not really. Like although we avoid computing higher order differentiation, which takes like p squared, but we see that in this form, this will take O and p squared. right? Because we're going to compute this outer product for each per sample gradient, which takes p squared, and there are n of them. So in total, it takes n p squared, which is like even slower than just computing the second order differentiation. And also inverting still require like PQ because this is still a P times P matrix as well as storage. So like why is this helpful? So the reason this is helpful is because we can like if we view or if we think about replace Hashim by FIM, then we can like exploit some of the structural assumption built in the neural networks. So for example, we can assume something like layers are independent. So if we assume this, then the FIM matrix will be block diagonal, and hence the inverse of that will also be block diagonal. And we know that we can compute the inverse of block diagonal matrix efficiently. So if you like to see the figures, this is what we are doing before we introduce this structural assumption. So we're going to form this fully dense covariance matrix by doing this outer product between or covariance between per sample gradients and average them. And we take the inverse for its P times P matrix, and we do the product with each of the per sample gradients. But now, if we assume there are structures there are structures built in the neural networks, namely, if we assume layer-wise they are independent. So for example, the first block corresponds to the first layer, and the second block corresponds to the second layers. So we see the covariance between the first block and also the second block, or the first layer and the second layer. If we assume they are zero, then the only non-zero term will be this these diagonal blocks. And we see once we assume that, we can take the inverse by literally just taking the inverse of these smaller blocks. And we can also do the products with the per sample gradient layer by layer or block by block. So this will become like very efficient. And to see the actual computation gain, let's say we have like L layers, and each layer receives like roughly the same parameters. So each layer receives like roughly P over L parameters. So each block is now P over L by P over L. So we can basically replace OP by P over L as previous like inverse FIM complexity and also product complexity. Like there's really nothing we can do about the vectors, because to compute the gradients, we are required to spend this much of time. But for the other two, like inverse FIM and products, we are only going to take like P over L, or we can substitute P over L back to our previous complexity. But you should like find out that there's an L missing in the denominator. This is because there are L layers. So you are multiplying L at the end because you are going to repeat this computation L times. And same for the storage. To store the vectors, there's nothing really you can do, but to store the inverse FIN, you can just store this, or you're only going to spend this amount of memory, right? Because like each block is P over L times P over L, and they are L blocks. So this is like P squared over L. Now you should ask, okay, this seems nice, but is this enough? And the answer is that probably not, because P is typically very large. So like computation-wise, inverse FIM still takes like this much time, and storing vectors is also very challenging. Like it will still take like OMP, which let's say for a 1 billion model, which is considered, I guess, like moderate, if not small, and with like 1 billion data points, you are going to spend like 4 exabytes, which is just infeasible. So the main bottleneck now becomes the large P for this per sample gradient calculation or storage. So a natural question or natural direction we should think about is, if we can operate with vectors of dimension k, which is much smaller than p, then we should be good. Basically, that means we can replace all the p in this above computation or complexity by k, with probably some computation overhead to do this like compression step to compress vectors down to like smaller dimensions. So this is like exactly what we're going to talk about, which is so-called gradient compression. So the intuition is literally just what I said, which is you want to compress the gradient, which I'm now going to denote it as GI, down to some like G tilde I, which is of dimension K, that is much smaller than P. So sure, the intuition is nice, and you seems to have a strong motivation, but now you should ask, is this even possible? Because what's the or why can you just directly replace and like known vectors by like small vectors, right? So the possibility of this compression is motivated by the following, which is like quite well known, I guess, in computer science. That is a so-called like Johnson-Lewis lemma. It basically tells us that um, given n vectors in high dimension, we can project them down to like logarithmic dimension while approximately preserve all this like pairwise distance or pairwise inner product. Or like if you like more intuitive explanation, that basically tells you that you can compress all the vectors down to very small dimension without breaking or destroying all the geometric structures. So this tells us that like for simple operation, for example, in a product, which is like roughly what we're like doing, we should be able to like integrate the compression algorithms that emit this JO type guarantee with our influence function computation. Like there's more complication here because we're actually doing more than inner products, right? We're doing like covariance, inverse, but you can see the like more elaborate discussion in this work, which is like a little bit beyond our discussion and beyond the scope. So yeah, I'll leave it there, but if you're interested, definitely check it out. So now the natural question you should ask, like this is a small detour, is that why is this new? Or why can we also apply the gradient compression in HVP computation in the optimization context, which is like, let's say, Lisa. So the reason is the following. Previously, remember, we said that the application they require or they consider requires HVP literally. So you should read this as they are trying to update parameters with condition gradients. So if you now compress the HVP result, at the end, you are going to get the compressed version of condition gradients. But now you are trying to use this compressed gradients to update your model, which means you are going to need to decompress it. So basically project this back to parameter space, which is like mathematically impossible, let's say. But now in influence function computation, we are not going to directly use HVP result, right? We're going to take in the product between HVP and this gradient of f, the gradient of the target function. So overall, like operating on small vectors makes no sense to optimization-related application. But in our case, this is fine because at the end, if we also apply the same compression to the gradients of target function, we can just take inner product without any problem because of the JL guarantee. If we are using compression method that guarantees or that have like JL guarantees. So that's why like we can use gradient compression in our case, but not in the, let's say, optimization context. So with that in mind, we can now look at some of the like naive implementation of this idea in, let's say, influence function computation. So first, I should like probably give you an example of what type of compression method will admit JL guarantee. And the most like simplest example might be just random projection or random matrix projection. So think about a linear map induced by this like random matrix, which is of size k times p, such that each entry is sample RID from some random distribution, let's say normal, random normal, or random marker distribution, which is just plus minus one with equal probability. And there's like famous theorem tells you that if you sample your projection matrix in this way, then you can apply your compression on this, the notation here we're thinking about like for the else layer. So for one particular layer, you can do this. And it says with high probability, this is going to preserve this like inner product structure or satisfy the JL guarantee. So I want to elaborate on a little bit on the dimension of this projection matrix, because now we're thinking about like else layer. And in the rest of our talk, we're also going to think about like per layer all the time. So it's worth spending some time on this. So in particular, GIL is now like P over L, right? We're thinking about each layer receives roughly the same amount of parameters. So GIL is like of size P over L. But now what about the compressed gradient? So we're thinking about in total, we have K budget to form our like final compressed gradient. if they are L layers, then each layer will receive K over L budget for the target dimension. So that's why like the projection matrix is of the size K over L times P over L. So with this like notation or with this understanding, we see that projection time per GIL is literally just metric vector multiplication, which takes like KP over L squared, right? KP over L squared. So in total, if we consider all data points, which is n data points, and all layers, which is L layers, random, which is this method that is like just dense matrix projection, takes MPK over L. So if you put everything together in stage 0, we're going to first compute the percentage gradient, which is like OMP for computation. And storage-wise, we're not going to store them. Instead, we're going to compress them immediately. So we know it will take us like MPK over L by random, and we are going to store them in only like ONK space. Because now we're only storing this like compressed gradients, which is of size K. And then we're going to compute RHVP using this compressed gradient. So now we can basically replace all the computation complexity before with K to replace P. So you can check, no, this is like nothing else but replacing P with K. So if you enjoy figures, it is something like this. So first, we're going to do forward backward pass, which span like O and P to compute all those vectors. And then we're going to compress them, which takes O and PK over L. And we are going to use this like compressed gradient to do all the FIN, inverse, and products. So to understand, like, okay, so this is now the full picture. But now I want to focus on this stage because this is the computation overhead we introduced in this whole pipeline, right? Before, without this pipeline, we're just going to use this GI to form our FIN and to do inverse to do the products. But now we're introducing this like additional stage, which takes like O and PK over L. So we want to understand like how much is this. And yeah, that's the computation time for random. And this is just like some reference. So to provide some context to understand how much time this will take, I would like you to think about how much time OMP is. So this is roughly one training epoch, right? So think about this. When you do one training epoch, that basically means you are going to go through the data set once. And for each data point, you are going to compute the percentage gradient. This is not exactly because we're not going to update the model, right? We're just going to compute the gradients, but then not actually updating the model. So this is roughly one training epoch. So we see the random takes like training epoch and how many of them, which is K over L. But now K over L is like roughly 4,000-ish. So K over L is interpreted, like remember, this is basically per layer projection dimension, which is roughly like 4,000. So we see the overhead is actually like 4,000 more epochs of training, which is like basically infeasible. Think about like the current, let's say, foundation model. Even in like, let's say, Anthropic, OpenAI, they're only going to train their model, let's say 1 or 2 epochs. Like, there's no way we can do like 4,000 epochs of training, or there's no way we can afford that. So how to speed up the overhead of compression, right? This is like now becomes our like main bottleneck. And natural idea is just to search for faster compression algorithm. And you see like there's a lot of compression algorithm that is faster than just random. And one alternative or one famous one is the so-called fast transcendent transform, which is used by Track, and you can check it out. But basically, it will reduce the projection time for per GIL down to this expression. So if you do not care about the log parameter, so log factor, and you think about K is much smaller than P, then this is basically P over L, right? So in total, for all data points and all layers, this will take like roughly O and P. So this is like roughly the same as one training epoch. I won't go into detail how to implement FGOT because that's like beyond the scope. But you should know like this is the previous state of the art before our work. So this is like roughly an additional training epoch overhead. So in total, this looks something like this. Okay. Now, a natural question you should ask is, how can we split this up further? So uh, to think about or to even like start thinking about this problem, we should probably step back a little bit and to see what's the issue when we use, let's say, just random, which is just like projection matrix based compression, right? So the problem really is like it is dense, like the projection matrix is dense. So think about, because each entry of P is sampled ID from this like plus minus one. So matrix multiplication will naturally take Kp over L squared. Remember, this is like what we derived. But in picture, this is something like this. So this is your P, which is like dense, fully dense. There's nothing zero here. Every entry is either 1 or minus 1, let's say. And then we are going to multiply this with your like input or your per sample per layer gradients. So if you take this in the column viewpoint of matrix vector multiplication, this is exactly this. So to read this, this is the first column, and you are going to scale or multiply this first column or weight this first column by the first dimension of your inputs or of your gradients. And you do this for every column and for every input, right? So this will correspond to this. The second one will correspond to the second column. And at the end, you are going to add them up together to get your final compression. So a natural idea to speed this up is to sparsify your projection matrix, which leads to the so-called sparse Johnson-Linguistic transform, or SJOT. So in particular, think about, let's say, instead of like making the projection matrix fully dense, instead, let's take only S of them to be non-zero. So let's say S is like, let's say 1 or 2. Then SJOT will take only P over L if S is a small constant per GRL. And we see that this is proportional to input size. If this is not clear, then look at the picture. Right? So now we're thinking about each column only contains like, let's say 1 or in general S, but we're thinking about S is a small constant. So let's say 1. So in each column, there is only one non-zero entry. So if you expand the actual matrix vector multiplication, this is exactly what it is, right? So for the first one or first column and the first dimension of your inputs, you're only going to do one operation and then add to the corresponding dimension of your outputs, right? And you do this for every column. So if you really think about this, then you should be convinced that this is equivalent to the following. So for each entry of your inputs or of your gradients, you are randomly selecting one of the output entry or output dimension, and you either add it or subtract from your like output gradients. So think about your output gradient is initialized as O0, and you iterate through like each dimension, and then you do this like randomly select one of the output dimension and either add to or subtract from it. So if you're not convinced, then you should pause and compare this slide and the previous slide, and to convince yourself this is exactly what's happening in SJOT. So why is this helpful? This is helpful is because SJOT not only depends on the input dimension, P over L, right? For every input or for every dimension, you're only going to constant amount of work. So the computation time scales with your input dimension, which is P over L. So per GRL costs only P over L, and in total, it costs only MP. So this is truly one epoch of training. And another nice thing is there's a potential speed up, which is that SJOT can exploit input sparsity. So in reality, it will run only in number of non-zero of your inputs. So to say this, also consider like if this is 0, right? If this entry is 0, then what you're going to do is you can just directly skip this point, right? So when you iterate through your input, you see this is 0, and you just skip it. And you see this is 0, and you skip it. So you see the input sparsity actually helps SJOT. In particular, it can be potentially faster than OMP. And this is our like benchmark result on our CUDA implementation of SJOT, where we benchmark between like different sparsity of your inputs. So we are manually making the input sparse. So we see like in the fully sparse regime where I think this is like 10% of them are non-zero, we can beat the dense matrix-based projection in all regime. But let's say in the fully dense regime where the input is not sparse, we start to beat, let's say, the PyTorch matrix vector multiplication-based compression on, let's say, 1,000 dimension. And the reason why we cannot beat them, like although theoretically we can beat them, but in practice we cannot in this smaller regime is because this is like custom CUDA kernel implementation, so there will be some overhead. So that's why. And also think about like PyTorch. It is like matrix vector multiplication, so very fundamental, and there's a lot of low-level optimization going on. So that's why it's hard to beat in small problem dimension. But basically, we're trying to say our implementation is also very good, and it start to beat this like highly optimized CUDA implementation of the provided by the PyTorch at around, let's say, 1,000-ish projection dimension. So now you should ask, is this the end of the story? Because like the SGOT scales with, or the computation time of SGOT scales with the input dimension. So if you are going to read through the inputs, this is the lower bound, right? But the thing is that this is not exactly true because if you think about like if you allow some lossy compression, then we can sort out some information. So basically, it means instead of compress everything succinctly, let's say what if we just select a few parameters to look at and sort out everything else? And why this work is that in the literature, people sort of find out that only few parameters are important. So this leads to like this famous hypothesis that is called like um, lottery ticket hypothesis, right? So if you're familiar with it, then you know what I'm saying. But basically, in the literature, people find out that this seems to be a reasonable approach to look at the parameters of the model. So you can think about this as a compression method. So by neglecting information or by neglecting some of the parameters, we can get a further speed up. So in picture, it looks something literally like this. So given the input, instead of read through each dimension, what if we just predetermine which dimension we're going to look into and then pick them out, right? So we see we term this mask because we are thinking about like this is basically the same as masking some of the inputs and only take out the non-masked inputs as our projection result or compression result. We see that this takes only O of K over L, right? This literally takes only proportional to output size. So this seems very hard to beat, right? Because it only depends on the output dimension. And if you are going to write to some outputs, this is the lower bound. So you see like per GRL costs only like K over L, and in total it costs only NK. So you see that we finally achieved this is the so-called like sublinear compression, which is like even less than read through the input. And to compress, we basically don't even need to read through all inputs. Instead, we only the complexity is dominated by outputting the results. So this complexity should now be impossible to beat. Right? But another question you should now ask is in what cost? Because this seems to be very crude compression. So let's step back a little bit and just look at the situation now. Now we have like SGOT and mask as our two candidates. And where for the first one, for SGOT, the computation time scale with input size. For mask, the computation time scale with the output size. And I probably forgot to mention this, but SGOT actually admits JL guarantee. And so basically that makes now SGOT has a strong guarantee on this like sort of preserving pairwise geometry. So it is very good compression guarantees, but the cost will correspond or will proportional to input dimension. On the other hand, mask is extremely fast with the cost only proportional to output dimension, but we will lose a lot of information. So now the question is, how can we combine them? So if you are like some sort of like very sensitive to the figure, then you might guess what I'm about to do. You can concatenate them together. and get best of both worlds. So the intuition here is that you can first mask to a moderate dimension, let's say K prime over L, where K prime is larger than K, but much smaller than P still. Okay, so this is like much smaller than P, but like still larger than K. So in the first stage, we're not losing too much information. But now, SGOT can succinctly summarize all the information in this like moderate size vector down to our final projection result. Okay, so why does this work? It's because we see now the time for a mask proportional to the output dimension and time for SGOT proportional to input dimension. So time is now just K prime over L. And so we term this as GRASS, which is gradient sparsification and sparse projection, where for sparse projection, for sparsification, this is corresponding to mask, where we're thinking about we sparsify the inputs. So this just takes like K prime over L, and for sparse projection, which is SGOT, this will take as well K prime over L. So in total, it will take like K prime over L. So if you consider like all data points and all layers, GRASS takes only nk prime. Okay, and now you should always remember like K prime is larger than K and much smaller than P. So if we summarize everything again, for the same thing, you are going to compute the perceptual gradient, which is stage 0. Nothing you can really do here. But now to compress the gradients, you can use GRASS, which takes only nk prime, and for storage, you are also going to store like only nk, right? Because the compressed gradient is of size k. And the same for the stage 2, which is IFVP computation. So in figures, it's something like this. Now we reduce this compression from NP down to nk prime. Okay, and k prime is much smaller than p, so this should be a good speed up. And this basically concludes the first part of the paper, which is the state-of-the-art compression algorithms. Now, let's step back a little bit and look at like a particular layer, which is linear layers. So why linear layers? So this is because like in modern model architectures, linear layers usually contain most of the parameters since this is dense, and also gradients of linear layers has nice structures. So due to the above, many have looked into how to accelerate all the computation we mentioned before in linear layers specifically. So for example, if you know, KFAC, EKFAC are all trying to expose this idea, and also the same for Gauss inner products, which basically tells you that you can do batch per sample gradient computation. While we are not going to talk too much about this, but what we're going to see will basically be the fundamental ideas of all these works. But let's first recall some of the basic facts about linear layers and see how we can like improve. So think about we have a model which contains only one linear layer, which is basically corresponding to logistic regression. So you have a weight of the layer, which is W, and have an activation function, let's say sigma. So the forward pass is basically this, right? You have an input, you pass to your linear layer, which is W times Zi gives you the output, and you pass it to your activation function, which gives you the prediction. And for backward pass, you are first going to compute this like gradients with respect to the prediction, and then you backwards times with the derivative of your activation function. You get your gradient with respect to the output, and now you further propagate to get the gradient with respect to your input. If this is like too complex, then we can look at a figure, which is essentially what we just said. Like you have an input and you right multiply with W, you get your output, and you pass into your activation function, you get your prediction. And for backward pass, you are first going to compute this and then back propagate to times with your gradients or derivative of your activation function to get the gradients with respect to the output. And then you left multiply this with W, your weight, to get you this, the gradient of the input. So this is essentially what happened when you do like forward backward pass in linear layer. But I want to note that what we actually want is the gradient of the layer, right? So it is the gradient with respect to the layer parameter, which is W. And if you do the chain rule, you'll see that this GI, which is exactly what we care about, is actually VI times this, the gradient with respect to this output of the linear layer. Okay, so keep that in mind. So if you generalize this a little bit, so let's say we have L layers, and for each layer, for the Lth layer, we have like WL, then the forward pass is just this, and backward pass is basically the same. We basically just add an L as an index and track the index more carefully. This looks complicated, but in figures, this is still something very similar to the previous figure, right? You just like chain this to the next layer. And same for the backward pass, we are going to treat this as the gradients with respect to the prediction. But now this becomes the input of the next layer, and you do the backward pass. And again, what we actually want is the gradient for the layer. So this is a gradient with respect to the layer parameter, which is the same as the input times the gradient with respect to this layer's output. Okay, so if you if you notice this, then you should see the problem now. The problem is that in a computation graph, when we are doing forward-backward passes, we never materialize GIL. Right? So in the previous figure, we're going to materialize this, and we are going to store this, store this, store this. And when we do backward pass, we're going to store this, 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 and this. But we never actually materialize the gradient with respect to the model parameter. So hence, our previous analysis completely neglects the cost of computing GRL, that is, computing this tensor product. So in picture, this looks something like this. So basically, there is a step of materializing per layer gradient for linear layers. And then after that, we can do our compression. So this is the step that we neglect. And now we're interested in, okay, how much overhead does this add? Okay, so assume like WL is roughly squared. So think about this as like this WL receives parameter which is roughly P over L. So the input and the output is of dimension roughly square root of P over L, right? So input and output is roughly of dimension square root of P over L. And when you do the tensor product of size P over L, sorry, square root of P over L, the cost will be this square. So it's just P over L. So overall, this is for one sample for one layer. So if you want to materialize all samples, all layers, it will take O and P again. So we see that even if grass takes only O and K prime, which is much smaller than O and P, once we need to consider materializing GIL, it will overall take O and P. However, like you might ask, okay, is this really a concern? Because how can you compress GIL without materializing it? And it seems like this OMP is not big of a deal, right? It just like lay in the background when we do this like stage 0, which is the forward backward passes. Like sure, there's in like stage 0.9, which is the preparation stage, that corresponding to materializing the linear layers gradient. So you can basically just view them together, right? So the reality is always harsh. There's one paper called Logra, which tells you that there's one gradient compression algorithm that does not require materializing GIL. So what does that mean is they don't even need to go to this preparation stage. They can basically omit the stage and directly do compression. And how to do that is actually very simple. Their intuition is that to compress GIL, instead of first materializing it and compress it, what if we just first compress each component individually, right? To compress this gradient, what if we just compress the individual factors to form this like final compression? So like think about, again, allocating these K over L budget for the compression. The target dimension for each like subproblem for both is square root of K over L. So we see that this is exactly how logarithm works. So instead of first materialize that, or materialize GIL and then compress, they will first compress each individual factors down to square root of K over L. And then they will reconstruct this like so-called compressed gradients from these compressed factors. And this will in total give you a size of K over L compressed gradient, which is exactly what we want. So now you see that they can just initialize in compression algorithms that takes input from square root of P over L to square root of K over L. Okay, so we set up for linear layer L by assuming the compression can be factorized or can be decomposed, and they can basically do this like sort of factorized version of compression. And in particular, their compression algorithm can be any compression algorithm, right? So they basically consider the simplest compression algorithm, which is random. So you see, since they are just like matrix vector multiplication, if you go back to this, they're going from square root of P over L down to square root of K over L. If this is just random, which is matrix-based multiplication compression, it will just take square root of Kp over L, right? So square root of Kp, everything over L. And we see that in the end, when reconstructing this, via this tensor product between two compressed factors, which is of size square root of K over L, the time of that is the whole thing square, which is K over L. And this is much smaller than square root of Kp over L, right? Because P is way larger than K. So this step is basically can be neglected. So now per GIL cost only square root of Kp everything over L. Now, if you consider all data points and all layers, logra only take n square root of Kp, which is smaller than np, and then they neglect the needs, or they basically overcome the needs to materialize the gradient. So we see they basically bypass this preparation stage, and the whole compression algorithm takes only O of n square root of Kp. So now what? We can summarize the situation a little bit. So for general layers, sure, GRASS is very efficient, and it will take ONP plus ONK prime, even if we consider the cost of materializing GI. So this is still the fastest gradient compression algorithm so far if we consider general layers, not specifically linear layers. However, for linear layers, GRASS will take ONP, which is the cost of materializing GI, plus this like ONK prime. But logra takes only L of n square root of Kp without this ONP, which is corresponding to materializing GI. So overall, logra beats GRASS by a lot for linear layers. So the next natural question to ask is, okay, what if we just focus on linear layers? Can we beat logra? So naive idea, if you pay attention to this point, you should probably think about what if we just replace the random they use in the factorized projection with GRASS? The answer is like theoretically, yes, we are going to get some speed up, but in practice, no. And to see why, it is because like two projection problems are too small. Remember, the two projection problem is taking gradient or taking factors of size square root of P over L down to square root of K over L. So to think about this or to ground the understanding, the actual problem size typically is like 4,000-ish to like probably 60. And random is extremely fast. Like remember the benchmark results we talked about like a while ago, right? This is extremely fast. Like this problem size is like nothing. So matrix multiplication based provided by PyTorch is already extremely fast. However, for our GRASS, as GOT's practical implementation suffers in this like small problem size. Remember, we have overhead, and also we have hash collision, which is like more technical. But you can think about this as like we are basically doing atomic add from a lot of input dimension, which all maps to or trying to add to a single, let's say, output dimension. This might be like too technical, but this is essentially what's happening. So SGOT basically suffers from this sort of like small problem size since we're using our custom CUDA kernel. So in practice, if we want to get actual speed up, we cannot just directly substitute random with grass in this factorized projection. So what should we do? The intuition is like, okay, what if we just apply SGOT to moderate dimension? Sure, but what does that mean? So we exploit this intuition and propose this so-called fact grass, which is factorized version of grass. So this is essentially what what fact grass looks like. First, we do same thing as log, but instead of doing like random, we use mask to first max down to like a moderate size factors. Okay, then we materialize this factors. So we do this tensor product to construct a larger input size, which we know will benefit SGOT in practice, right? Then we can do our SGOT to map the whole thing down to our target dimension, which is K over L. Or if you think about, if you still want to think about this as like square metrics, you can think about this as like square root of K over L times square root of K over L. But essentially, we are going to map the whole thing and stretch this out and pass it to SGOT and project it down to our target dimension. So now you should ask, okay, what is the complexity of this like new algorithm design? So first, we'll do specification, which is still masking. Okay, so masking will take, remember, masking will take the same amount of time of this output dimension size, which is square root of K over L, K prime over L this time, right? Square root of K prime over L. And for reconstruction, we are reconstructing two vectors, or we are doing tensor product between two vectors of size K prime over L. So square root of K prime over L. So overall, it is this square, which is K prime over L. And now this is the output size of this reconstructed masked vectors. And for SGOT, we know the projection time corresponds to the input size, which is K prime over L, right? So overall, it will take still O and K prime, right? You sum them all up and you see that the compression time for all of them is K prime over L. And now you times this with N and L, which means you consider all data points, all layers, which takes O and K prime, which is same as grass, but without materializing GIL. So you see, we basically came up with an faster algorithms, or not faster, but basically the same complexity as grass, but we bypass this preparation stage again, just as log graph. And we can summarize everything a little bit. So there's a sublinear compression-based influence function algorithm with an overhead of O and K prime, where K prime is much smaller than P, but slightly larger than P. And moreover, this extends to linear layers, which is just backgrounds. And we know layer-wise gradients are never materialized. And if you care about the comparison between fat grass and low graph, we provide a small analysis here. But basically, this means in basically any practical scenarios, our fat grass is faster than low graph. You could take a look at here, but essentially, all this is saying is K prime can be very large and we can still be low graph. Now we should see some experiments. So the goal of the experiment is very simple because we care about the speed and also accuracy of our method. And so we divide our experiments in two parts. First part is quantitative study, where we focus on smaller models and data sets, where we can measure the accuracy of our attribution methods more, let's say, in a more principled way. And this is, we are going to use some metric that is called LDS score. If you are familiar with this, then you know what it is. But if you don't know, then it's also fine. You can look it up to the, I think it is in Track's paper. But essentially, the higher the LDS score is, the better or the more accurate our attribution score is. Okay. And then for efficiency, we're going to compare the wall clock time between projection. And then we go to the qualitative study, which focus on larger models and data sets. And for efficiency, now we consider throughput, and for accuracy, we consider, let's say, a case study of how qualitatively our, let's say, identified most influential data point, which is the data point that receives the highest attribution score, is relevant to our input. Okay, so let's first see the quantitative study. So first, we're going to look at the this example, which is just MNIST track. So we do not include graphs because we are thinking about providing more like an ablation study to see how individual component of graphs perform with the baseline, because this is such a simple task. So you can see individually they perform very well already, right? So even for mask, just doing mask only, LDS score is also comparable to only baseline, right? So FGOT random LDS of mask can match them. But for the time, mask is the most efficient one. And you see for SGOT, we actually beat FGOT and also random by a lot. And we got the best LDS score. And now you might ask, what if we want to see the performance of graphs? So this is the second one, which is on ResNet 9 on CIFAR2. So we see the same trend basically follows. So mask is still the most efficient one, but now the performance falls short a little bit. And for SGOT, this is still very competitive, but now the time is like also still faster than baseline, but not as fast as we wish, right? But we see if we now consider graphs, this is just like slightly longer or slightly worse than mask, but like a lot better than SGOT. And if you compare to FGOT, this is like 1,000 times better. And also we achieve like let's say comparable ODS. Like this is like not as good as SGOT or FGOT, but the time is like much faster than both of them, which is like exactly what we are talking about, the best of both worlds. And the same trend can be found in these following two experiments where they are like more larger scale. I think this is like around million to 2 million parameters, and this is like 120 million parameters for GPT too small. And here we actually consider block diagonal FIN, which means we are going to use flat graphs. And the same trend basically holds here, but I think we should probably pay attention to this one because this is the more interesting one. You see, mask is still the most efficient one, and the SGOT is the most accurate one, but it suffers a lot. You see, like because we are now considering basically what I said, we are substituting the factorized projection just simply by SGOT, and we know SGOT suffers in small dimension, which is exactly what is going on here. It is actually worse than random. But you see, if we use flat graphs, we can still see like a considerable performance gain compared to log-graph. Like log-graph is the state-of-the-art compression method for linear layers, but now we can beat it by like 3 times faster, and we can still get like a comparable ODS. Next, we consider qualitative study, and we consider like llama 3 and 3.18 billion on, I think, open web text, and compare this to a log graph. Okay, and we measure the time by throughput, which is like tokens per second. We see for compression, we can basically beat log graph again by like roughly 3 times. And for the overall computation, we can beat it by, I think, overall like 20% or something like that. And if we just look at the absolute difference, we basically outperform log graph by like 160%, right? But roughly like we are achieving like 3 times more throughput. And finally, we look at one of the qualitative study we provided in our paper as well, which is we look at the most influential data points identified by flat graphs and see how relevant it is to the inputs of the large language model. And the left-hand side is what large language model generates, and the right-hand side is the data set or is the most influential data point identified in the data set, we see there are a lot of like similar word phrases, which means background is like, let's say, qualitatively accurate. So I think that wraps up all the talk. So thanks for listening. And yeah, if you are interested, you can reach out to me by, let's say, my email or just leave a comment. Yeah, thanks for listening. And these are the reference if you're interested.